Hi everyone, we are Team 21022, also known as the Grasshopper Harvester Phase 3. My name's Cecilia Stacer. I'm the team lead with a major in engineering management and a minor in systems engineering.
Hi, I'm Elena Ball. I'm the team procurement lead. I'm a major in biosystems engineering with a mechanical engineering minor.
Hi, my name is Ping Kai. My major is electrical and computer engineering, and my minor is math.
Hi, my name is J.R. Dodge. I'm studying mechanical drafting at Pima Community College.
Hi, my name's Anthony Hazoo, and my major is electrical and computer engineering, and my minor is engineering management.
Hi, my name's Emma Huffman, and my major is biosystems engineering.
Hi, my name is Jake Vartanian, and my major is in mechanical engineering.
The sponsor for this project is Gagi Davidowitz, and our mentor is Claude Merrill.
Shown here is our Senior Design Day poster.
Farmers across Arizona are plagued by grasshopper infestations, which reduce yield and damage crops. Organic farmers are unable to use conventional pesticides, leading to an opportunity for innovation. The sponsor has requested a solution to remove grasshoppers from crop fields that is cost-efficient, remote-controlled, and relatively compact. The Grasshopper Harvester is in its third phase at the University of Arizona. Shown here is Phase 1, Phase 2, and Phase 3, which is our phase.
Here are our functional and system requirements. We have 4 functional requirements, including remote control, storage, frame, and collection. Our system requirements include cart battery, grasshopper removal, weight, and capture mechanism, to name a few. Our system block diagram shows that each subsystem is connected to one another. The outside boundary line shows the external inputs to the Grasshopper Harvester system, including the user, which communicates to the remote control system, and the grasshoppers, which are sucked through the collection subsystem. The team follows Agile methodology, which includes sprints, for us defined as every 2 weeks. We meet together to discuss tasks that are achieved, not achieved, any impediments and improvements we can follow, and risks that have been incurred.
The following tasks were prioritized by the sponsor's request. First, an MVP, which was a remote-controlled cart that was delivered by mid-October. Second was steering and speed improvements. And third was a reduction in weight and size.
The following is a verification flow diagram, which follows the prioritization of the sponsor.
The current design is a 36 by 36 inch frame constructed out of 16 gauge steel. The steel frame weighs approximately 21 pounds. There are 2 non-motorized caster wheels welded to the rear of the cart and 2 motorized bicycle wheels in the front of the cart. Shown here is the current cart design. This is the steel frame that is used in our design. This is a SolidWorks drawing of the custom motor mounts that we fabricated. And here is the capture mechanism from Phase 2. The priority of Iteration 0, or MVP, was a fully operational remote-controlled cart. It was delivered on October 18th of 2020, and it utilized components from Phase 2, with the exception of newly purchased steel for the redesign of the frame.
The result of our first trade study is shown here for a diode. The team needed a diode to protect the polarity of the motor driver.
This is the Phase 2 proposed steel frame. And this is the steel frame from our MVP. This is a portion of the frame analysis conducted by the team on the MVP steel frame. We conducted analysis on E-strain, displacement, and stress. The analysis showed no hotspots or points of fracture on the frame, so we continued with our fabrication.
These pictures show the MVP's profile and front view. This video shows our MVP cart turning using skid steering. 2 wheels on either side move in opposite directions in order to turn. And here's a video of our MVP cart driving with an average mile per hour of 3.2. Here you can see a slow motion video of grasshoppers escaping the shop vac during our test day in Sonoyta, Arizona.
The priority for Iteration 1, or Version 1, was to improve the steering and turning of the cart. The only new component from this iteration was the diode, which was talked about previously, and our design was extensive research and a trade study for our squared wheels. This was delivered on December 10th of 2020.
This is the results of our trade study to purchase a new remote control transmitter. The previous remote control transmitter from Phase 2 did not meet the requirements of the sponsor. Here is a profile view of the Version 1 cart seen with squared wheels on the MVP frame. This is a video of our Version 1 cart turning using optimized skid steering with the squared wheels on our rectangular MVP cart frame. The turning is massively improved.
The priorities for iteration 2, or version 2, was improving the steering and turning of the cart and decreasing the weight of the cart. New components for this iteration included the purchasing of 16-gauge steel for a redesign of the frame to be fully squared, and new caster wheels to mount to the rear of the cart. We also performed motor research and new motor purchase. This was delivered on March 16th of 2021. The team again performed a stress, strain, and displacement analysis on the new steel frame design. Pictured is the E-strain rendering, which had a differential of 0.1 times 10 to the negative fifth in comparison to the MVP frame, and showed no hotspots or points of fracture.
During iteration 2, the team performed a 2 versus 4 motor trade study and showed that there was a significant improvement using 2 motors and caster wheels compared to 4 motors and bike wheels. During iteration 2, the team also performed a trade study on the new motors, which resulted in the purchase of the Grasshop 55018 motors. This is a video of our version 2 cart turning and driving utilizing caster wheels and demonstrating significant improvement in steering with no decrease in speed.
The priority of iteration 3, or version 3, was to improve the steering and turning of the cart. New components include 2 new Grasshop motors. This iteration's design process focused on the implementation of the new motors and speed testing. This will be delivered on May 6th of 2021.
Here's a video of our version 3 cart turning and driving. We're still utilizing the caster wheels and in the process of validating speed due to some motor issues. The initial speed test run was about 6.4 miles per hour, over double our MVP speed. Shown here are the profiles of all 4 iterations of the Grasshopper cart. Improvements can be seen in each version due to agile methodology. Here's our current SRVM. We're in the process of still testing 1.1, 3.3, as well as 3.4, 2 of which you can see were previously failures, 1 of which is currently in progress due to the motor issues we are incurring.
The team learned lessons throughout each iteration, such as electronics failure, weight constraints, and speed optimization. These were solved through incorporating a diode, redesigning the steel frame, and implementing new motors to meet the sponsor's needs.
The team will deliver the user manual as well as the Grasshopper Harvester and other documents to the sponsor by May 6, 2021.
The Grasshopper Harvester will be delivered with the hardware necessary to effectively collect grasshoppers from both crop rows and native grass areas. The team has worked to verify that the machine will operate as per the user manual and is prepared to offer possible improvements to the project for the sponsor. The team, despite facing struggles due to COVID-19, was able to effectively communicate and deliver a product to the sponsor that satisfied the determined system requirements.
Team 21022 would like to thank our sponsor, Gagi Davidowitz, our mentor, Claude Merrill, and Mike Mason at the BE Machine Shop for their support this year. Thank you, judges.